So, good morning, everyone, and thank you for joining us for the second webinar in the PoDIUM's Living Lab series. Today, we will be diving into the German Living Lab, where we will be looking at some of the preliminary results from the German use case, which is Cooperative Corridor Management in the city of Ulm, involving multi-connectivity. My name is Sevi Christoforou, and I am the Communications and Dissemination Officer at ICCS, the Institute of Communication and Computer Systems in Athens, Greece, which coordinates the PoDIUM project, and I'm also the dissemination desk leader for PoDIUM. I'll be the moderator for today's session. And before we begin, just a very quick note that you can always submit your questions at any time during the presentations using the Q&A option that you can see on your control panel. However, we will be addressing all the questions together at the end of the webinar. So for today, we are really happy to have a really good lineup of speakers representing leading universities and companies in Germany that drive innovation in connected and automated mobility. And for introducing them, you already have your webcams open, very efficient, thank you. So first, we have with us Michael Buchholz. He's the head of the research group's electric mobility and connected driving and connected infrastructure groups, and also a lecturer at the University of Ulm. Next, we have Stephen Schulz. He's a senior system specification engineer and also a project lead for funded projects at Nokia. Then we have Amr Risk. He's a full professor and he's the project lead at the Universität Duisburg-Essen. Then we have Alexander Seibler. He's a research assistant at the University of Ulm. And last but not least, we have Christian Eilers. He's a software development engineer at Robert at BOSS, sorry. Well, thank you all for being here, and would not want to take any more of your time. I'm excited to hear your insights. So without further ado, Michael, the floor is all yours.
Thank you, Sevi, for the kind introduction. I will just share my screen. One moment. I hope you can see it now.
Yes.
Great. And so I will give a short introduction in the German Living Lab and the use case that Sevi already mentioned, which is about cooperative corridor management. Let me start, because I'm not sure if all of you are familiar with the project. Let me start with a very short introduction of the PoDIUM project as total. It's a European-funded project with 26 partners. We have 8 countries involved in a total budget of 12 million. And the duration is from 2022 to 2025. So next year will be our final year with the final demonstrations. The scope of the project is to enable connected and cooperative automated mobility under real traffic conditions. And we have several enablers from the infrastructure side, like advanced multi-access edge computing. We work on data fusion and to build enhanced environment models. We work on ITS messages and to extend them for our use cases, because not all of the standardized messages today are sufficient to realize the use cases in all the different living labs. We are also working on software integrity and trust, and also data truthfulness within the different use cases. And we integrate vulnerable road users into this connected and cooperative traffic system. And we demonstrate this in urban and highway use cases in overall 3 living labs, one in Spain. There was a webinar last week. Sorry if you have missed it. But I think there is a possibility to inform you on our website. Then we have the German Living Lab, which will be introduced here. And there's an Italian Living Lab, and the use cases from the Italian Living Lab and the Living Lab as is will be presented in a webinar in January. Yeah, and we worked on the physical and also on the digital level, the overall architecture. It's a very high level view, but it shows quite good what we are working on. Is on the one hand, we have this edge and cloud layer with a global data management, but also local data management for the edge computing part. And it's a hybrid one, so we can move data from one end to the other. And then we have the road level with the different road users, which could be either directly connected to this edge or cloud via a cellular network, but also via roadside units and ad hoc networks like ITSG5. And also using the ad hoc networks, road users could communicate between each other. And we can also have sensors in the infrastructure, which are also connected by one of the possibilities or by a wired line to the data management, which perceive information about road users which are not connected themselves. So either the connected road users can report us about those unconnected ones, or the infrastructure can do so. And based on this, let's say, physical structure of how everything is connected and the communication structure, we work on different platform services, like in our case, environment modeling and platform management. Other use cases are working on priority for emergency vehicles, for example, in the other use cases of the other living labs. And over all layers, we have a software integrity and trust layer. And there will be also one talk later on how we handle trust in the environment model building by my colleague Alex. Now coming more detailed to the German Living Lab. Here on the right side, you see an image from Google Maps with a place where we have installed a pilot site. This was taken from previous projects, and we have improved and advanced it for the PoDIUM use case. It's an infrastructure pilot site where we have especially camera sensors and some radar sensors at lampposts, and each of the lampposts has a designated sensor processing unit, so a computer that pre-processes the data. And then we have object detections, which we send to a mobile edge computing server, mainly over the 5G network by our partner Nokia. The pilot site itself is operated by us, by Ulm University, and the radar sensors are provided by Bosch. And within the area of this pilot site, we drive tests with different vehicles. We have connected automated vehicles from Bosch and also one from Ulm University. And we also have a connected via a smartphone, a connected a road user on a bike, so a bicyclist, which is provided by Nokia. And because multi-connectivity is one of the topics we are working also on in this German use case, I think this is the only use case in the PoDIUM project where the real multi-connectivity approach, including scheduling, is worked on, which is done by the colleagues from University of Duisburg-Essen. And we also installed a 60 gigahertz Wi-Fi connection in addition to the 5G network. The 5G network by Nokia was enhanced by an additional mmWave 5G network in the area of the intersection or this pilot site. And we are, from the previous projects, we are also operating an ITSG5 network there. So we have multiple connectivity possibilities from the road users to the infrastructure and to the edge server in the end. And what we want to show is the use case of cooperative corridor management. I will introduce this use case on the next slide. We have two different scenarios, and corridor management means what you see on the right side here. One of the lanes, so it's a two-lane road, so one lane for each direction, and one lane is blocked maybe by a truck that is, I don't know, broke down or is just parking there because he needs to unload cargo or something. And now we only have one lane left for both directions. And in this first scenario, you see a connected automated vehicle coming from the north part, and for which the lane is blocked, and there's another one coming from the south. And now a cooperative plan could be that the vehicle coming from the south, so from the bottom, agrees on stopping to let the vehicle coming from north pass this obstacle so that it's safe to pass the vehicle and without causing any incidents. over there. This is done by a cooperative planner, so it's not a pre-distinct rule, but it's analyzed which is the best solution for the current traffic situation, which of the vehicles should wait, which should drive, and this is the first scenario. And we have two different versions of this scenario. We have the baseline version where the infrastructure sensors are also used, and we have we call it lightweight solution because we want to research on the possibility to realize such use cases even without infrastructure sensors, if enough connected and automated vehicle with sensors on board are available, and to realize this use case even without infrastructure sensors, just on the basis of the objects that the two vehicles perceive. And then we have a second scenario, which is very similar, but from use case overall, but we have exchanged one of the connected automated vehicles by a bicyclist. The bicyclist could come from south or from north and also wants to pass this obstacle. We want to make sure that the bicyclist can safely manage this scene and is not endangered by any of the traffic participants. And so we also want to ensure safety for this bicyclist. And because this bicyclist does not have sensors to perceive the area around here, this scenario will always be done, including the infrastructure sensors. That are the two scenarios in our use case, and that's it for my talk. And now I will hand over to Steffen, who will talk a little bit more about the 5G mmWave network that Nokia built up on the test site. Thanks for your attention. And Steffen, please go on.
Thank you, Michael. So let's open my presentation. So, okay, hello everybody. My name is Steffen Schulz from Nokia in Ulm, and I want to talk about the usage of the 5G mmWave from CCAM and present first results.
Steffen, sorry to interrupt. We cannot see your presentation.
Okay, sorry.
It's okay.
Yeah. Oops.
Now we can see it, or we can see your screen, not the
Your
presentation.
screen.
So.
Yeah.
Super.
Oh. Okay. Millimeter-wave or frequency range 2 is defined for 5G between 24 and 40 gigahertz in 4-band. At the moment, there's no significant commercial usage in Europe, but in North America and Asia Pacific. Currently, mmWave networks are used in 3 scenarios. The first one is fixed wireless access. That means the last mile to the home is realized by mmWave instead of copper or fiber. The next would be hotspots to enhance capacity in dense open areas, and this is used mainly by smartphones. And the third one are special usage in enterprise or private networks. The main advantages of mmWave is on the one hand the high throughput, bigger than 4 gigabit per second, could be also more, and the very small latency, less than 5 milliseconds. We have also disadvantages. The main disadvantage is the small coverage with less than 1 kilometer in radius, together with the high penetration loss in buildings. The second one is the limited availability of the user equipment, like modems or smartphones. In the PoDIUM project, 5G mmWave is used together with other communication technologies in the German Living Lab. So Let's have a look on the network installation in the German Living Lab. For mmWave, we have to use a non-standalone 5G installation because of the availability of modems. That means we have a LTE anchor cell with centimeter wave. That is in band 41 with 2.6 gigahertz TDD. And additionally, 5G millimeter wave radios. The centimeter wave, you can see on the picture here, the installation is located on the German Red Cross building. On the map is here. And we use this sector to the Living Lab as the anchor cell. And the millimeter wave is directly installed on the intersection. There are 3 sectors, each for every direction of the T-junction. For millimeter wave, we use band 258 from 26.5 to 27.3 gigahertz. And we use a bandwidth of 8 times 100 megahertz. So, as already stated, there is a lack of commercial user equipment for millimeter wave, especially for the European frequency bands. In the project, we are using an evaluation kit of Quectel, which includes centimeter wave and millimeter wave for non-standalone communication. Inside this kit is a modem from Quectel, the RG530F European version, and the used chips on the modem as a Qualcomm SDX65. This evaluation kit includes also antennas for centimeter wave and millimeter wave antenna array with together of 128 antenna elements. For our test, we have used the installation on car, here on the left-hand side, with only 1 modem. And for the CAFs in the project, we have a weatherproof installation with 2 modems for front and rear direction. And on these pictures, you can see the installation of the car of the University of Ulm. So now let's have a look on the first results using the millimeter wave connection. On this slide, one can see a drive test with the latency results. Ping between the car and the edge server was used. And in the Living Lab around this T-junction, we have passed the streets always in both directions. Red is the connection to the LTE anchor cell, and blue millimeter wave with less latency, mostly around 5 milliseconds. In this picture, we can also have a picture of the coverage. To the north, we have from the T-junction, we have coverage around 150 meters. To the east, around 150 to 200 meters, and to the west, around 300 meters. Next test result is the downlink throughput measured by iPerf between edge server and car. Like for latency, the red marks the centimeter wave connection, and the other colors are related to different throughputs for millimeter wave. The best values are in the direction to the T-junction, and up to 2 gigabit per second can be reached, restricted by the capability of the modem. The last measurement shows the uplink throughput from the card to the edge server. And here the maximum throughput is larger than 230 megabit per second. Let's sum up. We have a successful installation of mmWave with 3 sectors in the test area in Ulm. The cars are equipped with mmWave modems and antennas, and first test results about coverage, latency, and throughputs are available. The main result is that mmWave can also be used locally in areas like intersections for communication with moving vehicles. The next steps is the further optimization of the mmWave installation. For instance, handover between the mmWave cells directly, and the further integration of mmWave communication in the PoDIUM use case and for function offloading. Thank you for your attention. And now let's hand over to Amre.
Right. Thank you, Stefan. I hope everyone can hear me.
Yes.
I'm just trying to share my screen right now. Okay. Okay. Are you able to see my screen?
Yes,
Yes.
perfectly.
All right, great. Okay, from my side, welcome to this part of the webinar on the German LL. My name is Amre, and this part is on the multi-connectivity-based adaptive data traffic steering for cooperative corridor management. So to remind everyone of our communication architecture, given the talk by Stefan right now, and given that he introduced the number of technologies that we, types of physical layer communication technologies that are available in the German LL. We have the following overview, which consists of having cellular mobile 5G network with centimeter wave and millimeter wave cells. We have an ad hoc Wi-Fi in the area of the test site that operates in the 60 gigahertz band, and as you see here, between the vehicles and roadside units, and we also have the roadside units connected to the MEC using wired connections, as well as the 5G centimeter wave connection. In this part of the webinar, we are talking about multi-connectivity to, for example, enhance the redundancy, or enhance the reliability using redundancy. So basically, we use this redundancy of the multi-connectivity to either enhance the bandwidth. We could use the multiple physical layer technologies in parallel and split the data between them, or map the same data on the different technologies to enhance the reliability. This brings me to an overview of the types of the communications that we have. So we have in the PoDIUM project, in general, single connectivity, multi-connectivity, and hybrid communication defined. So using, as the name says, a single technology between endpoints describes the single connectivity part. The multi-connectivity part, which we are concerned with here, is the one between devices that can use multiple technologies simultaneously. And if you are using multiple technologies simultaneously, you have to have also the ability to schedule messages, CCAM messages or data packets over the available technology. So you have to decide for each message or for all messages, to make it simple, how to use the communication technologies at hand. As set for reliability, availability, and so on. And we also have in the PoDIUM project hybrid communication defined, which where messages are simultaneously transmitted over all available communication technologies. Now, to our specific setup in the German LL, we have the following technical setup that you see on the right-hand side. We have inside of the vehicle OBUs. We have one that has the CCAM functionality. We have a so-called ComPC, which is an OBU that contains the schedulers, to which we will get in a second, and on the one hand side receives the data from the car PC that runs the CCAM functionality, and the other hand it maps this data or these messages on the different available technologies. So the 5G technologies, which actually consists of centimeter wave and millimeter wave interfaces, as well as the millimeter wave ad hoc Wi-Fi, or the 60 gigahertz Wi-Fi connectivity to the RSU, which both the RSU or the radio head or the radio access network both route the received data to the MEC, where we have on the other side also a scheduler implemented that takes care of demapping this data and forwarding it, serializing it to the CCAM functionality. Now, this technical setup, as I just explained it, does not only include the ComPC and the interfaces then, but it also includes this scheduling software that does the mapping and possibly duplicates the packets and drops duplicated packets for serialization on the receiver side. When we faced this question at the beginning of the project, so if I use only one slide to look a little bit back, we looked at different options for realizing these schedulers, and we have had academic work beforehand where we had looked at different multipath scheduling models and possibilities to program those, and in general you can discern either schedulers that are in user space on a protocol level, something like multipath quick, for example, which are very flexible and easy to program, however slower. And we have schedulers as a software switch on these ComPCs, which is restricted. However, it runs at line rate, so it runs basically as a switch, and it can sustain much higher rates than a protocol such that MP-Quick. And it is also programmable in terms of you can change the rules that schedule packets to paths also at runtime. So you can basically change the mode, and that's also the title of my talk. So you can change the mode, for example, from duplication to not duplication whenever you need this at runtime. Now, speaking of the realization, as said before, we have this separate communication PC, which is an OBU, and it runs the scheduler that is realized as a software data plane switch programmed with a domain-specific language called P4. It passes the packets from the CCAM functions and merges the client traffic in uplink and distributes the server traffic in downlink according to some scheduling rules that we will see that are applied to it. This is realized in hardware on the vehicles in the following setup, where we have a switch, and we have the car PC, and we have this communication PC that has a high number of interfaces. These interfaces are required because we have these directed communication or line-of-sight communication technologies that we use. For example, the 60 gigahertz Wi-Fi which has two modules, one that looks to the front of the vehicle, one that looks to the back of the vehicle. The same thing with the 5G millimeter wave, for which we have also a front and a back modem provided by Nokia, and we have in addition the centimeter wave, all connected to the car PC. Now, in terms of a software realization, this scheduler running on the comp PC looks as following. We have a usual Linux network stack running through which the interfaces are connected. We have a switch program that runs something that's called the behavioral model. And what it does is it maps interfaces to the real interfaces of the comp PC, right? And then beforehand, we write a switch software in this domain-specific language that is compiled and then written to this switch or programmable switch. And this software, what it does is it configures so-called match action tables. So every packet that comes on the left-hand side here gets parsed, and out of the packets, the headers are taken, layer 2, layer 3, layer 4 headers if we need. So let's stick to layer 3, and then we match on where this packet should go to and specify a specific action, right? And this specific action is that the packet, for example, gets replicated on a number of these interfaces, or all of them, or only sent over one of them. And after this action is decided, the packet, this is normal switching, so it has to depart, and then it departs out of the corresponding interfaces that are required. The one interesting thing here that I would like also to mention is that these configurations can be target specific and can be also adapted. So we have an API that makes it simple to change these this rule at runtime. Well, this brings me back to the realization, the final point about these scheduling rules down here, where you see that we are matching the incoming packets on predefined packet rules, basically, where we could say we could have rules of the form match on a specific type of message and map it to a specific number or specific interfaces, or match on another type of message and map it to other interfaces, or match all packets and map to all interfaces, which is full duplication at the end of the day. Right, so this brings me to basically the final slide of my talk. The message that I would like to stop with is that we have different type of CCAM data factor messages that have or might have different requirements in terms of throughput and reliability. So we can, using such an approach as we implemented it in the German LL of the PoDIUM project, have different grades of throughput and reliability, or different grades of mapping the messages to interfaces, and have an adaptive scheduling of the different streams. This provides, at the end of the day, a flexible and a model-based multi-connectivity. I have not had the time now to talk about the model-based part, but there is an academic work behind this where we can, as you see, construct multi-connectivity schedulers that allow us to explore the scheduling design and maybe even optimize where packets go or in which paths packets go. All right, so this brings me to the end of my my presentation part. I will hand over to Alex.
Thanks, Amre. So hi and welcome to my part of the webinar. I'm Alex Schäble. I work at Ulm University, and I will talk about how to build trust into the sources of our digital twin. So first, let me start with a description of the task of the digital twin. In our use case, the digital twin is responsible for the fusion of all dynamical information about the road and the road users from the different data sources, and it collects and fuses all this kind of information, and then passes this data to the cooperative planner, so the planner can react to the dynamic situation on the road. So there are mainly two types of data sources. First are the detections of the infrastructure sensors, and so we have a number of them installed on our pilot site, and all these detections get passed to the digital twin. And the second type of data sources are coming from the connected road users. There are three types of ETSI messages we are using here. First is the CAM and CPM messages from connected vehicles. Here the CAM messages describes basically the ego position of the vehicle, and the CPM describes the perception of the vehicle from their onboard sensors. The third message is the VAM, which is basically the ego position of vulnerable road users, and in our use case, this message is sent by the bicyclist. So now the digital twin fuses all this together, and so we have a complete understanding of the road situation. And to do so, we have a two-step approach, where we first fuse and track the information from all the infrastructure sensors with a model-based multi-sensor, multi-object tracking algorithm. And then we use this result of this algorithm and enhance it with the information from the CAM, CPMs, and VAMs. This two-step approach is needed because this different type of data sources have different statistical properties, so we need different kind of algorithms for the fusion of these data sources. So now let's look in the following. I look a little bit more into detail about the first part, this model-based multi-sensor, multi-object tracking algorithm. So first, what means model-based? This model-based means that we have explicit models for the sensors that we use. These models include, for example, the detection probability that a sensor has. The sensor accuracy is described, but also the clutter measurements. But also the behavior of the road users must be modeled in this approach. For example, we assume that a car is moving with a constant turn rate and constant velocity on the road. And then we use these models and together with Bayes' theorem, this algorithm is derived, and then we get a result, yes, based on the inference with these models. So this means we depend a lot on these models, and if we have good models with a good match between the assumptions in these models and the actual data, we can expect good performance from our tracking algorithm. And now this topic trust comes into the picture, because trust in this meaning, in this context, means that something behaves as expected. So if we know that our models for data fit well, we we trust this data source. We can trust it, and we know that we can expect good tracking performance. So now I present some methods to check these models for the sensor models. So here we only take a look at one part of a sensor model, namely the detection probability. This is the probability that a road user will be detected by a sensor, and it's Bernoulli distributed with some parameter PD. And the idea here is that we estimate this parameter PD or based on the live data we receive, and then we compare our estimation with the parameter we use in our tracking algorithm. So on the picture, you see in blue our prior estimation about the detection probability. Here, this prior estimation comes from our knowledge about the sensor. For example, we know that a camera works pretty good in if we have good weather conditions, so we can expect a high detection probability. And then we perform some tracking cycles, and so we can update our estimation, and we have our red curve. And now we see that we have gained some knowledge about this detection probability parameter because there's lower variance in our estimation. You know, and then we can check our compare our estimation with the parameter we actually used in our tracking algorithm, which is here this blue dot. And in this context, we can say that our estimation or that the parameter we used is okay with our estimation, and then we have we can say we have a good trust in this part of the model. And similar methods, we derived similar methods for other parts of sensor models, and this methods has been presented at the ITC and Fusion this year. So now we have some kind of trust in the sensor models for one sensor. We have to do this for all kind of different sensors we are using for the tracking. And then we also have this road user behavioral model. And if we know that all parts, we have trust in all parts of the models, we can say that we have trust in our tracking algorithm in itself. And then we have to do the same for this track-to-track fusion approach to conclude that we have trust in the whole digital twin. And to conclude, we know that if we have good models, we know that we have good digital, we have good performance of our digital twin. Okay, and that's from my side. And now I want to give the stage to Christian from Bosch.
Thank you, Alex. You should be able to see my slides now.
Yes.
Yes.
Right. So that's I will continue now with the part of the webinar functional design of the cooperative maneuver planner. So what's our goal on this part? Our goal is here to implement a real-time CCAM, so Cooperative Connected and Automated Mobility Service, specifically a cooperative maneuver planning service for ad hoc corridor management. And as described earlier, such an ad hoc corridor can be an urban traffic scene where, for example, a truck blocks part of a road such that vehicles need to merge onto the oncoming line, as can be seen here on the right scheme. Such a cooperative planning service has to utilize collective environmental perception that is reliable to safely orchestrate the road users through such a corridor. And to enable low latency communication, the service then deployed onto a Mac server. And you can see below on the scheme, there's a planning service, how the planning service integrates into our overall PoDIUM platform architecture. The main interfaces here are, for our use case, the ones to the digital twin and the one to the CITS methods and user handling module. Let's have a look now on how we design the cooperative maneuver planner. From a high-level point of view, its function can be described as follows. Connected road users signal their willingness for cooperation by periodically sending maneuver coordination messages, in short MCMs. And for each connected road user, the cooperative maneuver planner continuously analyzes the scene for potential corridors. When such a corridor or blockade is detected, the planner assesses the cooperation capability, determines a passing sequence, and computes maneuver suggestions for all involved road users. Now this next diagram provides more depth insight into our cooperative planner implementation. On the left, you can see the inputs to our module, specifically the MCMs from the CITS method, which contain state, road, and maneuver feedback. And on the right, you can see the MCM is also an output, but mainly the maneuver suggestion container is filled. The other inputs are the digital twin that was presented by Alex, and an HD map. These interfaces also match the ones shown in the previous platform architecture view. And one key benefit of these architecture or these interfaces is a low coupling and a modularity, which enables an efficient extendability for example, new CCAM services, as well as interchangeability of components. The functional key concept of our planner framework is a distributed approach for the corridor detections, coupled with a central module for the corridor cooperation assessment. The distributed here means that each individual connected agent instantiates a situation analysis and behavior planning job, whose task is a maneuver suggestion computation. The required corridor detections for the cooperation module are here the outputs, or rather even byproducts of the situation analysis. Let's have a more in-depth look into what the situation analysis looks like. Inside, a geometric approach is used by us to reason about the environment. It is based on the environment modeling of the planner framework, and specifically the object tracks, the occupancy grids, and the HD map. The outputs are behavior plans or behavior blue scripts that are characterized by sets of conditionally valid geometric areas along the road. And if an impassable area, such as the truck, is lane blocking due to being standstill and not moving for a while, it's marked as a potential corridor for the cooperation module. To now orchestrate the road users involved in this situation, the cooperation module sends some high-level behavior signals back to the planner instance, which then updates the behavior priorities and conditions. Finally, starting from the respective highest priority, the behavior are analyzed with respect to their feasibility. This is, for example, what ensures that in this use case, a yielding agent candidate can actually slow down and stop in time to let the blocked agent pass, instead of directly sending maneuver suggestions and waiting for feedback and have the loop closed inside the planner. For the cooperation assessment, very briefly, it determines the set of involved road users driving towards the corridor. And next, it assesses the cooperation capability based on time of arrival and yielding feasibility, which was determined before by the planner. And it waits for maneuver acceptance of yielding road users before signaling the right of way to the blocked road user. As an outlook on the final result, I brought a snapshot from one of our preliminary tests on the pilot side. On the left here, you can see a connected agent that needs to leave its own lane and get onto the oncoming lane. And on the right side, we have a yielding agent that was detected by the cooperation module. And give some more insights here. The CAV has a lane blocking corridor detection in front of it and a non-blocking secondary corridor detected farther down due to the extended visibility information. And now the behavior planning or situation analysis module now can plan a maneuver around these two corridors, and it finds out that it has this lane blocking corridor, which we require a yielding agent, and we have the secondary non-blocking corridor detection where it already can pass through its own line. So the yielding agent has to yield only for the first lane blocking corridor. And what happens under the hood is that first the yielding agent gets a stop point here in front of the lane blocking corridor, and secondary the CAV, which is blocked, gets the maneuver suggestions around this corridor. And after both agents passed the corridor situation, the situation is considered resolved and the yielding agent can drive away. So that's from the planner side. Thank you for your attention.
Thank you so much, Christian. And thank you all for your presentations. I will ask you once again to open your webcams, and then we can also open the floor for discussion. For the audience, feel free to type your questions to the question box, and you can also indicate the speaker you're directing the question to. We have some minutes left, but I hope everyone is okay with extending a little bit longer if needed to ensure that we cover all questions thoroughly. I can start with one question. Christian, as we ended with you, maybe I can start with you for the questions. Could you perhaps elaborate, go a little bit more into detail on the types of CITS messages you're currently using for the planner, for the use case, and if you plan to incorporate any other types or formats beyond those currently used?
Yes, so for the planner side, we currently use mainly the MCMs, which are maneuver coordination messages. And these are derived from a previous project and not yet standardized in the ETSI. And the other input are the CPMs, which come from the digital twin. And for your secondary question, we don't intend to support more messages for the planner side. We instead try to use the MCM and extend upon this.
Maybe I can add for the overall use case. So also for building the environment, the digital twin, the environment model, we also use CAM and VAM messages. So vulnerable road user awareness messages and cooperative awareness messages from vehicles, and the vulnerable road users for the bicyclists. And also CPMs from the connected automated vehicles, sending their information to the digital twin and where everything is fused. So we have CPM, VAM, CAM, and MCM. And only the MCM is not standardized yet, and we base on our own proposal from a previous project, as Christian said. All the others are in the current versions, with some slight extensions, maybe for ranges of values, because they are too small for our use case in some parts. But this is already in discussion in the respective ETSI working groups to be extended.
Okay, super. If someone would want to have more information on this, is there somewhere we can, like, maybe a deliverable that we have or something?
I can't remember the number, but we have a deliverable where all the messages and everything is summed up. So it's in one of the deliverables. Sorry, I can't remember which one it was.
It's okay. We can share it with an email if
Yeah.
with the participants, and we can add it on the website. All right. Thank you so much, Christian and Michael. A question for you. The theory you described, the system. Have you analyzed it using a model?
Right. So let me just very quickly share my backup slide, which is here. So as I mentioned at the end of my my presentation part, that similar to the work of University of Ulm, we also have a model-based or a model basis for our part, which is based on the problem that we have streams of packets that we would like to transmit over different paths or different communication technologies under some constraint that we would like to keep. And without going into the details of the model, I would like to be very brief here. Our constraint is, for example, or mainly the delay. So we would like to minimize a quantile or a percentile of the delay, and we ask ourselves the question of what is the effect of the different rates, data rates that you get on the different paths, and the rate of the arrival of the packets. And it turns out that there is a model for this. I mean, without going into the details of the model, but there is a model of this that takes, and you only need to look at the left-hand side, the packet rate. So what is the arrival rate of the streams of messages, and what are the service rates of the different paths. And for a very simple model, you can get a nice formula at the end showing the impact of the different rates of the service and of the flows of the arrivals, and relate those to the percentile of the delay. So long story short, and let me get back to this formula, that you can say at the end, this is the way I would like to split my traffic over the different communication technologies, such that I adhere to some requirement on the delay. I hope I answered your question.
Super, thank you.
Yes, you can read about this in one of our publications that was there last year.
Okay, we could share this information with a follow-up email as well. And now perhaps one last question to Michael. How do you plan on proceeding in the coming months leading up to the demo? What key activities or milestones are in store?
So currently the last, let's say, component-wise evaluations or getting them running in the field and our pilot site and the vehicles are ongoing. And we have already started with some preliminary field tests for the use cases and scenarios, but not yet with all the components included. So maybe not using the scheduler, but only one of the communication links. So we have to put everything together for final overall tests, and that will happen in the rest of this year and also in the first quarter of the next year, and then our final demo. And the demo day, so not the final demo of the project, but the demo day for the German Living Lab is planned to happen in the beginning of April. And yeah, so everything should be running even before that, and there will be extensive testing especially, and also then afterwards the demo day there will be some test drives for evaluating the KPIs that we want to evaluate together with the other partners in comparison to the other use cases until the end of the project. And then we will have some videos showing the use cases and also the results from the KPI stuff in the final event, probably in September.
Sounds great. We're looking forward, and we will be sharing the progress as we go through the website. I think we're just in time, very efficient and effective. Before we wrap up, I would just want to mention that you can find additional information in the links that we have here. We will be sharing the slides and the recording, and also additional interesting reading about the use case with the follow-up email. So please stay tuned. And also, Michael also mentioned this in his presentation, but we have one last webinar in the new year, January 30th, about the Italian Living Lab. So we encourage you to register, and hope to see you there to end with the PoDIUM Living Lab series. And yes, I would like to thank you all a lot, and of course the great speakers for being part of this webinar. We will be sharing everything in an email. If any question comes up, feel free to reach out. And yeah, thank you for joining us again, and have a great rest of the day, everyone.
Thanks for your interest. Have a great day. Bye.
Thank you all.
Thank you.
Bye.
Bye.